Right, so now we're on to the second part, which is the pole placement part. So here's our transfer function that we had from the few minutes ago, and we've now, in pole placement, we have some desired poles. So we've got some desired pole locations that S is minus 10, S is minus 15, and S is minus 20. So we've got 3 pole locations which we could write down as a polynomial like this. And we could multiply this polynomial by that one to get one polynomial which represented that particular system. And this one comes out as s cubed plus 45s squared plus 650s plus 3000. Can check a few of these. That number there is going to be that plus that plus that. That number there is going to be that times that times that. So it looks quite, this one's that times that plus that times that plus that times that. So that's where the numbers come from. So there's our desired poles. Here's our desired poles multiplied in a polynomial factor. Then we actually work them out here. Now in pole placement design, we have a full state feedback controller, U equal to minus K1, K2, K3 times X1, X2, X3. This is the desired control system now. And our job is to work out K1, K2 and K3 so as to put the closed loop poles at these locations here. So this is this is quite straightforward. We can go straight to this equation really. And what happens is when we do the state space analysis, the K1 adds in with the first term here, the K2 with the second term, and the K3 with the third term. So we could get a desired, this is the desired behaviour. If we did feedback control on this system, the equation would come out as s cubed plus 45 plus K3 times s squared plus 13, sorry, it's these numbers again there, 13. So it's that number there, goes in there. And the next one will be 54. So it'll be plus 54 plus K2 times S, and finally 72 plus K1. That will equal to 0. So what we do is we put a K1 in with this one, a K2 in with this one, and a K3 in with that one. They go in reverse order, like all the calculations do here. They're reverse order calculations. So here they appear here, but when they go in here, they go in reverse order. So what we know now is that this term here is the same as that one, this term here is the same as that one, and that term there is the same as that one, which gives us 3 little equations for K1 and K2 and K3. So we get 72 plus K1 equals 3000. We get 54 plus K2 is 650. And we get 13 plus K3 is 45. So that's by saying this one is the same as that one, that's the same as that, and this is the same as that. We can then solve these for K1, K2 and K3. So it's going to give us K1 as 2928, K2 as 596, and K3 as 32. And then that's our design of our pole placement controller. Now again, if you wanted to, you could check this solution in MATLAB. So I'll just show you how to check the solution in MATLAB, because it is quite a simple little check. The first thing we've got to do is work out the state space equations for these. So we're going to have x1 dot, x2 dot, x3 dot, and we'll do it in companion form. So it's got a bit confused there. And we don't need the C matrix in this particular case. So what we know is, we know this is the A, this is the B, and we also have the desired pole locations, P, and we can put those as -10, -15, -20. So there's the three pole locations which we define as little array P. We could then put A equal, and then we can put this matrix in now, so it's going to be 0, 1, 0, semicolon, 0, 0, 1, semicolon, -72, -54, -13, close square brackets. Put the B in as 0, semicolon, 0, semicolon, 1. So that's got our A in and our B and a P. And then we can simply type in K equals place A, B, P, and it will work out K for us, and hopefully we'll get these little answers here. So this is a little 4-line piece of code that's very handy. That's C there. It's very handy for computing the pole placement controller. So the next thing we would go on from this now is looking at an observer design. If not all these states were available to design, we'd have to go on to an observer. So the next part of the lecture is going to be on observer design.